She carries up to 90 aircraft. She can deliver over 300 tons of bombs and missiles in a single strike. The USS Nimitz is the first of the Nimitz-class aircraft carriers, the biggest warships in the world. She owes her success to a century of innovation in shipbuilding. We've identified 7 landmark aircraft carriers, each pivotal to the evolution of carrier design. At the heart of each vessel lies a major technological innovation that allows carriers to grow in size. One by one, traveling up the scale, we'll reveal the incredible stories behind the inventions that enabled them to get ever larger. 7 ingenious leaps. From big to bigger, into the world's biggest. The Nimitz can steam at over 55 kilometers an hour, sail for over 20 years without refueling, and house 6,000 men and women. She can detect threats over 500 kilometers away and launch a supersonic fighter every 20 seconds to intercept them. She is a masterpiece of modern engineering. To understand how the Nimitz became the most powerful warship ever built, we must travel back to 1916. Almost as soon as people learn to fly, they want to try to get airborne from the deck of a ship. The ship is the 16,000-ton USS North Carolina. Reaching takeoff speed requires a lengthy runway. But the decks of warships are crammed with weapons and radar. There's no room for a long takeoff strip. So engineers must devise a way of getting an aircraft up to takeoff speed with a shorter runway.
The fundamental problem is down to a basic law of physics. If you want to launch a large mass in a short space of time or distance, you've got to give it a lot of stored energy very rapidly. This is the basic kind of technology that's been known for thousands of years, the slingshot. I store the energy by stretching the elastic. I put my aircraft in it, store the energy, let go, and it flies wonderfully. But of course, this isn't a real aircraft with a real pilot. The challenges of making it work in the real world are much more significant.
The solution comes from the fathers of aviation, Wilbur and Orville Wright. In 1903, they achieved the first powered flight and then developed their own launcher, a catapult. Their design consists of a 6-meter-high wooden tower. This holds a weight suspended from a rope. As the weight drops, the rope pulls the plane along a rail until it reaches takeoff speed. The Wrights offer their launching system to the US Navy. But dropping a heavy weight on the deck of a warship is not such a good idea. The Navy go back to the drawing board.
So they came up with a better idea. Another form of stored energy on board was compressed air, installed in warships for things like launching torpedoes and so on. Compressed air can be released and give thrust. So in a simple way, we can use compressed air to release an aircraft from a warship.
In 1916, the military tries the idea out on the battle cruiser USS North Carolina. The engineers build a 30-meter steel track at the stern of the ship. They use compressed air to shoot a piston down a cylinder. The piston uses a rope to pull the plane along the track. But compressed air alone is not powerful enough to launch an 800-kilogram plane. To speed it up, they feed the cable through a system of pulleys. These multiply the force exerted on the plane and increase its velocity by 7 times. After years of trial and error, they finally have a system that works. Until now, the might of a great power has been determined by the strength of its fleet of battleships. But now, the flimsiest biplane launched from the deck of a carrier can sink the most heavily armed warship. It is now the age of the carrier. Today, catapults are at the working heart of the USS Nimitz.
Without the catapults, we have no other means of getting the aircraft off to do their missions. It's basically just a giant slingshot.
It is the task of the shooter to tune the catapult to launch aircraft of different sizes.
As a shooter, my job is to take the weight of the aircraft and the wind that we actually have over the deck and use that to determine a setting that we put into our catapult system to shoot it off the front.
Lieutenant Kozlowski adjusts her catapult to launch a series of F-18 fighters. Each catapult has enough muscle to throw a Cadillac a kilometer. The secret of its power lies hidden beneath the deck. Instead of complicated pulleys and wires, the Nimitz has a pair of cylinders slung below its runway. Inside these cylinders are pistons. The pistons connect to the plane through slots at the top of each cylinder. They fill the cylinders with pressurized steam, which shoots the pistons and the plane forward. To prevent the steam escaping, they fit 2 strips of flexible metal that act like zippers and reseal the slots as the pistons pass through.
They'll salute us before we send them off the bow, telling us that they're ready to go. And then we'll hit the fire button.
On land, it takes over 1,500 meters to get an F-18 airborne. But the steam catapult does it in less than 100. In 1916, the USS North Carolina has a huge drawback as an aircraft carrier. She has nowhere for her planes to land. She must use planes that can land on water, but these must be winched back on board every time they fly. Hardly practical for a ship of war. Landing planes on the ship itself requires a long deck and a ship big enough to accommodate it. The 28,000-ton HMS Ark Royal. In August 1917, Royal Navy pilot Edwin Dunning attempts the first landing on a moving ship. The obstacles he must negotiate include the ship's central bridge and funnel, known as the superstructure. In a truly audacious move, Commander Dunning swoops sideways in front of them and lands on the front deck. 5 days later, he tries again. But as he touches down, the engine stalls and he loses control of the plane. The deck crew try to grab the powerless aircraft, but strong winds blow it over the side. Dunning is knocked unconscious and drowns in his cockpit. Commander Edwin Dunning proves that a deck landing is possible, but he pays the ultimate price. Making the deck safe for landing requires redesigning the ship's superstructure, the obstacle that had blighted Dunning's approach.
One proposed solution was to split the superstructure into two parts, moving them either side of the flight deck.
But the gap between the two blocks is hardly wide enough to allow a plane to land, and naval architects fear this will unnerve their pilots. They consider removing one of the blocks. Not such a good idea. So naval architects search for a way to offset the weight of the block they now call the island, to correct the ship's balance. They fill the port fuel tanks to the brim whilst only partially filling the tanks on the starboard side. But as she begins to run out of fuel, the ship starts to list again. Then they try moving the entire hangar to port, leaving behind an empty space. But the crew soon fills the void with equipment, and the ship regains its starboard list. Finally, they decide to physically extend the hull outward on the port side and shift the heavy machinery to balance the boat. After 2 decades of trial and error, they now have a truly revolutionary design. HMS Ark Royal is launched in 1937. The Ark Royal is the mother of all modern carriers. Her island sits on her starboard side, allowing a long, clear flight deck. Her layout sets the template for every carrier to come, including the Nimitz. Like the Ark Royal, the Nimitz is a giant floating airport. The island is her control tower, her eyes, ears, and brain. Within her nerve center on the first floor are the officers in charge of the flight deck. Above them are the radar and weather rooms. Above these, on the 5th floor, is the captain's bridge. He runs the ship from here in overall command of strategy and tactics. But on the top of the island, nestling just below the radar domes, sits perhaps the most important place on any carrier: primary flight control. Here, the air boss and mini boss run the business end of this warship. controlling the operation of her strike fighters.
ILARC lands, manned and ready, sir. List is 0.6, starboard down.
Okay, roger that. Thanks, appreciate it.
They control the busy airspace around the Nimitz, takeoffs and landings.
305.
But this is no ordinary runway. The flight deck has been called the most dangerous workplace on Earth. Here, the deck crew must dodge wings, blades, and jets as they fuel, arm, and park the multi-million-dollar warplanes.
Turning starboard, heel to port. Watch your moves, watch your step.
Engineers mirror the layout of the flight deck in miniature to keep track of the comings and goings of each aircraft.
L1, 404. We'll take him back to L4 and we'll stuff the hole right there.
It's literally nuts and bolts technology.
This is the Ouija board. This is a miniature version of the flight deck, and these little plastic pieces that we have here keep track of aircraft that we actually have out on deck. Now these nuts and bolts, they represent different things. This means that it needs an aircraft that needs to be turned, its engine's turned, and then this one means it needs fuel. It helps us keep track of everything going out on the flight deck since it moves at such a fast pace out there. They're constantly updating this board.
Got to get him out. I got to clean up L4. I've got to drop this guy down off into the hangar. And if you want, you can put 203 on the elevator. It really doesn't matter to me.
This is always reliable. If we have a power outage, I could always rely on this being up and running.
Hey, before you put something in L1, make sure it's got missiles on it, right?
The Nimitz can operate more aircraft than any other carrier in the world. Up to 90 lethal warplanes. But in 1938, HMS Ark Royal, the biggest British carrier, can only handle about 50 aircraft. But the American admirals of the time want double that number for their carriers. But there isn't enough room in their hangars to store them. So the deck must take the overspill. This is potentially disastrous if an aircraft coming into land doesn't stop at once. It takes years to resolve the problem. The solution will be built into the new 34,000-ton USS Hornet. From the time of the first carriers, engineers have been experimenting with ways of slowing planes down by snaring them with so-called arrestor wires.
Well, the earliest systems consisted simply of ropes attached to pairs of sandbags. And the aircraft would come down and engage this rope, but of course one set of sandbags was not enough to stop a heavy aircraft. So as the aircraft proceeded down the flight deck, it had to engage successive pairs of sandbags until there was enough resistance to stop the airplane. This simple system, of course, was nowhere adequate for high-performance aircraft, so other more complex systems had to be developed.
On the USS Hornet, they must stop an 8,000-kilogram warplane landing at over 135 kilometers an hour in just 45 meters. This is how they do it. As a plane comes into land, a hook on its tail snares an arrestor wire and pulls it forward. Beneath the deck, this action forces a ram into a cylinder filled with fluid. This fluid dampens the plane's momentum as it is squeezed up a tube and through an opening, made ever smaller by a closing plunger. An elegant solution. But in practice, snagging a single wire proves difficult for the pilots to do. So the engineers line up several wires, one behind the other, to increase the chances of a successful grab. But even this doesn't guarantee success.
During the Second World War, it was fair to characterize the landings as looking like a controlled crash. As the pilot approaches the back of the ship, he's going to fly his airplane into position just above the wires, and then he hopes that the airplane will drop right into the middle of those wires and pick up one of those 12 wires. If they didn't catch any of the wires, then they had 5 what they call Davis barriers that would engage the landing gear on the aircraft and stop it that way. Unfortunately, these Davis barriers normally would flip the airplane upside down, but it would definitely stop.
Today on the Nimitz, trapping an arrestor wire has become even more challenging. Jets hit the deck traveling at 225 kilometers an hour, giving a pilot precious little time to guide his plane onto the wire. It's so difficult that pilots must practice over 100 simulated landings before they're allowed to try the real thing.
Now, landing on a carrier is a lot different than landing at a long airfield with a 12,000 or even a 5,000 foot strip. This is what we call the dirty configuration. I've got my gear down, my flaps are full, and my hook's down, ready to catch the wire. And there's no mistaking it. When you catch wire, it's a lot like a mild car crash. It throws you forward in the straps, and you definitely know that airplane's going to stop.
The principle behind the arrestor system hasn't changed in over 60 years. But the Nimitz pushes the system's braking power to the limit. It must bring a 25,000 kilogram F-18 traveling at 225 kilometers an hour to a stop in just over 100 meters. About the length of a football pitch. But even with 4 wires to target, the pilots sometimes miss altogether and must go round again. They call this doing a bolter.
Or a bolter is when you've got your hook down with an intention to land and the jet doesn't stop. You may have a couple of choice words as you're going back flying again, and you can probably picture all your buddies down here watching the pass and horse laughing you.
You fail miserably and then you get heckled by all your friends for the rest of the day.
To give a bolting pilot the chance of a clean getaway, the landing deck on the Nimitz angles out to sea, away from the parked aircraft. To help perfect their skills, senior pilots stand at the stern, passing judgment on each landing.
We will grade them on their start, the in-the-middle position, at the in-close position, and then again as they cross the ramp.
And then the grade goes into an overall grade point average for how everybody's doing.
Every pilot in every squadron thinks they're the best.
Definitely me.
Yeah, it's this guy. Who's the worst pilot?
That guy.
The arrestor wire allows planes to land safely on a crowded deck. But during World War II, the deck itself becomes a target for enemy bombers. Defeating them demands a total rethink. A carrier twice as big, the 61,000-ton USS Midway. June the 19th, 1945, a naval catastrophe. Japanese bombs penetrate the USS Franklin's wooden flight deck and explode in the hangar below. 724 American sailors and airmen are killed. The Navy resolved never to allow this to happen again. protecting the crew by replacing the wood with armored steel sounds simple enough. But this causes huge problems for ship designers.
When you replace a deck made out of wood with one made out of armored steel, your real issue is to do with adding top weight and making the vessel top heavy. This causes the vessel to reduce its stability, which makes it vulnerable to capsize in waves.
To make the ship more stable, the hull must be wider. But a wider hull meets more resistance than a thinner one and impedes the ship's movement through the water. To restore speed, they must make the hull more streamlined. This makes the ship sleeker and longer, but also heavier. The mighty USS Midway is the product of this thinking. It weighs in at almost twice the size of her predecessor, the Hornet. For the decade after World War II, the Midway is the largest ship in the world. She stretches nearly 300 meters. Almost 12,000 square meters of 9-centimeter thick steel plate protects her flight deck. This is just an 8-centimeter chunk from it. She weighs in at 61,000 tons. The USS Midway is so strong and well protected that she serves for 47 years. The deck of the Nimitz is also steel, but it isn't armor-plated. It doesn't need to be. No attacking aircraft should ever get close enough to drop a bomb on it. Layer upon layer of high-tech protection stands in the way. First, long-range radar scans the sky for intruders. Should there be any, she directs her fleet of F-18 fighters to intercept and destroy them. If an enemy missile does manage to elude her aircraft, it will meet her next line of defense. A ring of missile-armed warships. Finally, the Nimitz can unleash her own missiles, each capable of destroying anything that gets within 8 kilometers. The tactical team runs this high-tech shield from a bunker deep within the Nimitz.
We can protect ourselves from great distances with our airplanes all the way down to in close with our point defense systems.
Should it all fail, the captain knows he can fall back on a trusty technology from a bygone era.
We have 50 caliber machine guns that are manned by our crews here. We also have then layered defenses all the way down to the captain and the 9mm.
The Midway's armored deck gives her the security she needs, but her aircraft are outdated. In the 1950s, Navy commanders want jets on their carriers. But these bigger, faster planes cannot land safely. It will take 10 years and an ingenious idea before jets can routinely land on the 81,000-ton USS Forrestal. In December 1945, a jet manages to land on a carrier for the first time. It is an extraordinary feat of flying by Eric Winkle Brown, the Royal Navy's top test pilot.
That aircraft there is the aircraft that Winkle Brown landed in December 1945 and made carrier aviation with jet power fundamental to any modern navy. It also identified that there were a batch of new problems to be resolved.
The main problem is speed. Faster jets leave their pilots less time to find the correct angle of approach. If they come in too steep, the aircraft will hit the deck too hard. But if their approach is too shallow, they may clip the stern of the ship. Engineers discover the optimum angle of approach for a safe landing is 3 degrees. But it's almost impossible for a pilot to get this right every time. In slower planes like the Hellcat, pilots have time to respond to instructions from a man on the flight deck who uses paddles to help guide them down. Former Royal Navy pilot Nick Goodhart explains how it's supposed to work.
So we're curving in, and he thinks I'm a little bit too high. So he makes a signal, and I say, ah, yes, a little too high, and I throttle back just a little bit and descend a bit, and then he said, no, too low. And I open the throttle a bit, and sure enough, we're on a reasonably good landing track, and I get near the round down, and just as I'm coming over the round down, he makes the signal cut. And I chop my throttle, and we descend gracefully onto the deck, and everybody's happy.
At least that's the principle. But Goodhart discovers it to be a very dangerous procedure.
In fact, we lost so many pilots that way that it exceeded by far the number who were killed by the enemy in the war.
Appalled by such losses, Goodhart himself comes up with a simple idea that enables the pilot alone to find and follow the correct angle of descent.
We've got this rig set up here, which was the rig that I used originally in my boss's office. I set up a mirror, which I had borrowed from his secretary, on the carrier deck there, and that mirror has a line across it made out of lipstick to mark its middle. And I also had a torch, which we got here. So we set the torch up on the carrier as well. And then we invited his secretary to come in, and I said to her, look, now your job is, as a pilot, is to see the reflection of the torch in the mirror and walk very slowly towards it, keeping the reflection on the line.
By keeping the light level with the lipstick line, the secretary, like the pilot, will naturally follow the correct angle of descent. Translated onto a ship, this is what's happening. The torch is represented by 4 lights fixed to the deck. Beyond them is the mirror. A row of lamps represent the lipstick line. As the plane approaches, the beam from the deck lights reflects back to the pilot at an angle of 3 degrees. If the pilot keeps this reflection in the center of the mirror, he will come down at the right angle. But it's not as simple as that. At sea, a ship pitching in the waves throws the beam about, sometimes with devastating results. To stabilize the beam, they fix the mirror on a gyroscopic mount. Now a plane can safely follow the right line of descent, however rough the sea. Admiral Goodhart's mirror landing aid proves a great success, whatever the size and speed of the aircraft. It allows a whole new generation of supersonic fighters and nuclear-armed bombers to land on carriers. The Forrestal now truly deserves to be called the world's first supercarrier. Today on the Nimitz, they use an improved version of Admiral Goodhart's landing aid. Pilots call the central lamp in this row of lights the meatball. It is fitted with a special lens so that the approaching pilot can only see its light when he lines up his aircraft to come in at the correct angle. The system stands up well to the demands of modern warfare with its tremendous onus on night operations. On a clear night, pilots can see the meatball as far as 6 kilometers out. Even so, night flying is not for the faint-hearted.
I had 2 night landings last night, and I'm going to do it tonight, and I'd rather not. It's something that, with 250 night landings now, I don't look forward to it. And the knees still shake, and you're still breathing heavy and still breaking a sweat when you land.
Night flying can tax even the most experienced pilots. Trainees today are not allowed near a $20 million plane without conducting 10 hours of simulator rides first.
Well, one of the defining factors about naval aviation is when you take off from the boat, you have to land on the boat in all kinds of weather. Day, night, storms, sunny. Now at night, or in bad weather behind the ship, the instrumentation is critical. Right now I'm at 1.9 nautical miles. At this point, I can't see the meatball at all. I'm relying solely on my instruments. Again, on dark nights like this, where it's really rough, a lot of illusions out there, hardly any depth perceptions. It takes a lot of mental concentration. First step is to get in this aircraft below 250 knots. And then most importantly, I'm going to reach over with my right hand and I'm going to slap down the hook handle. It's pretty important because that hook is what's going to stop me. Trimming the aircraft up on nights like tonight, it can be a real heavy workload. The pace quickens, you're getting a lot of wind gusts. So the whole way down, I'm making small trim adjustments until I get it stabilized. About 1.5 miles, I can start picking up the lights of the carrier box, which is the landing area. It's a lot of concentration. Right now, at one of these nights when the pulse is racing a little, the breathing's a little heavier, working really hard here, really high. It's a great feeling when you pick up the meatball because now you know you have a good visual indication to the proper landing point. Right now, show me a little high. It's coming down into burner. There's a good trap. And as soon as I'm ready, when he comes out, give me the throttle back signal.
The mirror landing aid allows the USS Forrestal to carry the world's biggest and fastest Navy bombers. But as a fighting ship, she has a severe limitation. She runs out of fuel after only 3 days of action. The Navy searches for a new type of propulsion system. It is so massive that they must build a bigger ship to accommodate it. The 91,000-ton USS Enterprise. This is the start of one of the Navy's most dangerous operations, refueling at sea.
Go, heat around! Go, Roberts, get him out of his feet! Go! Together, heat around!
A conventional fossil fuel carrier drains her tanks in about 3 days, and then needs a pit stop. But this is no simple top-up. The crew uses a pilot rope to pull across the fuel line. Then, once the line is connected, they transfer more than 2 million liters of fuel. But that's only enough for about 72 hours of sailing. The process ties the carrier to a slow tanker, and leaves both vulnerable to attack by enemy aircraft and submarines. There must be a better way. One solution: harness the colossal energy released by the splitting of an atom to produce nuclear power. Scientists discover that firing particles at atoms of uranium loosens the bonds that hold their tiny components together. A chain reaction in the nuclear power plant in the bowels of the ship triggers a massive release of energy in the form of heat. This heat can then be used to generate steam. Shooting the steam through a turbine forces its blades to rotate at high speed. And transmitting this movement through a set of gears generates enough turning power to spin a 120-meter-long shaft attached to a propeller. Together with 3 other propellers, they have the power to push 91,000 tons of metal through the water at over 55 kilometers an hour. But nuclear power comes at a price. To protect the ship's crew from deadly radiation, the engineers have to shield the reactor with hundreds of tons of lead. But a supercarrier needs 8 reactors. In heavy seas, the extra weight sitting in the middle of the hull could cause the keel to buckle. So they strengthen the keel with a honeycomb structure of steel cells. These take the weight of the reactors and lead to the birth of the largest carrier the world has ever seen. The USS Enterprise takes to the sea in November 1961. Her 8 reactors make her the largest nuclear power facility in the world, able to supply the electrical needs of a city of 500,000 people. And she has one colossal advantage over conventionally powered carriers. She can sail for 3 years without having to be refueled. Today, a Nimitz-class supercarrier only needs to be refueled once every 20 years. She requires only 2 reactors to deliver the same power load to the ship. And the space that once might have been used to store fuel for her engines is now used to store fuel and ammunition for her jets. Her reactors also send power down 1,500 miles of cables to support this veritable city in the sea. 6,000 heads lie on 14,000 pillowcases between 28,000 sheets. Each day, cooks prepare 18,000 meals from their supply of 120,000 eggs, 15,000 kilograms of potatoes, and over 11,000 kilograms of meat. But it can be a lonely place.
The worst thing about it, being on the Nimitz, would probably be being away from family.
Being away from home.
It's the same day over Groundhog Day.
Every day is Groundhog Day. We always joke about it. Every day's Monday.
The camaraderie of the pilots out here is probably the only thing that makes it so you can survive with your sense of humor and with your sanity.
Over the past 30 years, this floating community has demonstrated its prowess by delivering air power straight to the heart of the enemy in conflicts around the world. The first Nimitz was commissioned in 1975. She was so successful that the US Navy ordered 9 more. But it took a long 7 years before the first one was built and ready for service. And there was only one dry dock in the whole of America big enough to handle a 99,000-ton Nimitz-class carrier. There had to be a quicker way of building the carriers of the future. Until 1981, the US Navy builds their carriers using traditional methods. They construct them like buildings, from the bottom up. One vessel requires enough cable to stretch from New York to Dallas, over 45,000 tons of steel, and an army of workers.
A huge range of craftsmen were involved. Boilermakers, shipwrights, carpenters, electricians, and so on. And that meant that the ship grew very slowly. It tied up a dry dock for a long time.
The electricians get in the way of the plumbers, who get in the way of the welders in the congested compartments. That's why it used to take 33 million man-hours to construct a carrier. Today, they build Nimitz carriers on the dockside, section by section, and then weld the pieces together afterwards. The specialist trades take turns fitting out each module with its cables and electronic systems, its bulkheads and passageways. And as they are no longer in each other's way, they build the ship much faster. A job that once took 3 hours to do in a traditional yard now just takes 1 hour using the new modular method.
Well, they're very, very large pieces that go together. The improvements in computer design, the ability to reduce the number of pieces that go together, it is going to be a heck of a lot more efficient.
They use the biggest crane in the Western Hemisphere to move the modules into position. 161 modules come together to make a carrier. Each can weigh up to 850 tons. Moving the modules pushes the gantry crane close to its lifting capacity. On July the 8th, 2006, workers crane the final piece of the jigsaw into place. It is the carrier's mighty 700-ton nerve center, the island. Finally, after 3 years of construction, the shipbuilders flood the huge dry dock. Mission accomplished. The latest and last of the Nimitz class of carriers, the USS George H.W. Bush, takes to the water. She is the culmination of 100 years of innovation in carrier design. Her deck is ready for the latest generation of stealth fighters. Her special bulbous hull greatly reduces drag. Lighter composite materials have trimmed the weight of her island. And automated systems have trimmed the size of her crew. The USS George H.W. Bush is truly a $6 billion man of war. Nimitz-class carriers are currently the biggest and most technologically advanced warships in the world. But already naval architects are working on the next generation of supercarrier. The first won't be delivered to the Navy until 2014. Until then, the Nimitz will reign supreme.